Okay, hi everyone. Today we'll continue the lecture that we started in previous class, and today we'll talk about the last part of the data acquisition system or the measurement system. So we said that we have the sensor that measures a physical phenomena, convert it into a voltage. Take this voltage, clean it if it has noise, and amplify it if it is low, and make it ready now for what? To take it to the computer. Now, before you take the signal to the computer, there is something in between, which is the data acquisition system. This is the system that will take your signal and make it adaptable to the computer so that the computer can understand. If you may say, it's like a translator. Computer cannot understand what we call as a continuous or an analog signal. Computers can only understand ones and zeros. So you need this card so that the computer will understand the signal that you are feeding from your measurement system. Now, when you buy or you want to buy a data acquisition system, there are certain specifications, certain things that you need to watch. You need to check before you select your data acquisition system. And these are the most important thing in the data acquisition system that you need to pay attention to while ordering or buying your data acquisition system. The first one, and in my opinion, this is the most important one, is the number of input channels. How many input channel your card can acquire? Let's say you want to measure temperature at, let's say, 10 different locations. So then you need to have a data acquisition card that can acquire these 10 measurements. So it has to have at least 10 inputs. But if you want to do only one or two measurements, that's all, then you don't need to have this multi-input channels. So this is the first thing that you need to check. And we call this is the analog input, meaning how many analog signal my card can take care of. And if you look here at the bottom, you will see these are some real specification of actual cards, okay? And it has different criteria. So for example, here, this is the analog input. How many? This has 8, this has 16. And the price will make a big difference. The higher the channel, of course, the more expensive is your card. Then we'll come to the sampling rate. Sampling rate, as I said, my signal is continuous. So I have a signal like this. This is in reality. This is called continuous signal. But my computer cannot take this. So I have to take samples, only certain samples. So if this is time, how many samples per second I can take? How many samples I can take per second? So for example, these two cards, they can take a lot. Their sampling rate is very high. It is this is the sample rate, 2 million samples per second. So in every second, you will take 2 million samples. So if this is from here to here, if this is the time is 1 second, you will be acquiring 1 million samples here. The question is, do I need that or not? It depends on the nature of your signal. If your signal, like in our application, in most of the time, the change with respect to time is pretty slow. We don't have something that change in nanosecond. Then I don't need to have such high sampling rate. Maybe I need 1 kilohertz per second, meaning 1,000 sample every second. That will be more than enough for me. So this is the sampling rate. And also this is a very important parameter that decide the cost of the card. The card can go from few hundreds to tens or maybe hundreds of thousands of dollars. So it depends on the sampling rate. This is one of the important criteria. Then we'll say about resolution. Now I will keep this in mind. In resolution, It says here 16-bit, 16-bit. How we relate the resolution to the number of bits. What is a bit? Keep this in mind. I will come to this later on. Input range. Input range, it means that if I am measuring a signal, what is my input that I can? What is the maximum? What is the minimum voltage I can use my card for? Usually it is from 0 to 5 volt, 0 to 10 volt. So that is the range of the voltage I can have. What if my signal is more than this? Maybe I am measuring a voltage with 20 volt. If I feed that directly to the card, I will burn the card. So I have to do something. We'll talk about that later on, so that to reduce the signal magnitude. Analog output, that's not very commonly used by people who work on measurement. This is usually, we use it if I want to send a signal from the card to the outside world. Okay, same thing, digital input and digital outputs. Now, the difference between the analog output and digital output here, I can send a signal with certain magnitude, 2 volt, 3 volt, 4 volt. It depends on the range of the volt that I wanna do. Why I need to do that? For example, if I have an LED light emitting diode, and I want to make it light, but I don't want to make it on and off, but I want to have it at different intensity. I want to have the light at different intensity. So I will control this by controlling the analog output. But if I need it, I want it to be on and off only, then I will use digital output. And there's also digital input. Sometimes we want to measure only ones or zero, on or off. So these are the main criteria of a data acquisition system. And as we move on, we'll try to understand more and more the implications of the sampling rate, resolution, and so on and so forth. Now, this is the example. This is how the card that you will be using, which is a microcontroller. You will be using a microcontroller in the experiment. And although here it looks very big, hopefully everyone got their microcontroller. So it's a pretty small one, but it is a very, very efficient data acquisition system. Cost-wise, few dollars only, but it can do a lot of things that is, for us, for this course, is more than enough. So it has the analog input. This is I just talked about. And it has from A0 to A5, it has 6 analog inputs. So I can use this card to do up to 6 measurements. And also I will have a range of digital input and output. 13 channels can be used, or 14 channels can be used to send or receive digital signals. Also, I have a power, 5 volt and 3.3 volt. If I want to get voltage from this, for example, to feed my circuit, I want to have 5 volt or 3.3 volt, I can take it directly. You can see here, this is the 5 volt, and this is the 3.3 volt. I don't need to have a battery, okay? And also there is a ground for our reference. Now, this is the USB, this is your connection between the card, okay, and your computer, so that you can transfer the code from the computer to your microcontroller. And power in. Now, if you wanna have after you upload, you connect this to your computer, the USB cable, okay? So this is the USB cable. So you connect your card to the computer. Why? To upload the code here on the microcontroller. Now, when you connect this cable, you are getting also power. This needs power as well to be able to work. Now, once you upload, you don't need the computer anymore. You already have the code here. So you can disconnect it from the computer and then connect your battery to the power in, so that you can have it completely separate from your computer and does whatever you program to do. And you will see these things as you progress in the lab. Now, let's talk about the most important and basic function of the microcontroller or the data acquisition card, which is the analog to digital conversion. As I said, I will be measuring temperature. Temperature, it will have something like this. This is how it look like. This is the time, and this is the magnitude. So it's a continuous signal. My computer will not understand. I have to change this from this analog format into a digital format. So what I need to do, I need to do some sampling. I need to do the conversion. Okay. So in your card, this is the the card, and here it does. This is the chip that does the A to D conversion. You don't need to worry about it. It does that by itself. So this is the analog signal. This is sinusoidal analog signal. Now I will take samples from the signal, okay? And then after that, I will convert these samples to ones and zeros. And I will come to this. This is where it comes the resolution. Okay, I will come to that later on. But now this process from going from analog continuous into sample, taking these samples at certain time interval, depending on how fast is your card doing this sampling or the sampling rate of your card, you will have this type of signal. Okay, now a problem that can happen when you do the sampling, we call it aliasing. What is an aliasing? Now, this is my analog signal. Imagine if I am just taking 4 samples per cycle. So in every cycle, this is one full cycle. I'm taking only 4 samples. So I'm taking this sample, this, and this sample. So we connect the dots. So you will have a completely distorted signal. So this is what we call aliasing. You are distorting the signal, the original signal. What to do? You need to take more samples. So if I take per cycle 8 samples, see here, now it's much better. If I take 16 samples, way better. Now, how the signal look like, it will have certain saturation level. After a while, there is not much improvement. So this is why you need to know, based on your application, what is the sampling rate that you need. Sometimes you don't only distort the signal, but you require a different signal. This is an interesting example. The dotted line is my original signal. And because I'm taking very low sampling rate, I'm getting a sinusoidal. However, this sinusoidal has a totally different frequency than the original one. So I thought that, okay, I'm getting the signal, the right signal, but that's wrong. Your signal is much faster than your sampling rate. So this is what we call aliasing, and can lead to either distortion or getting completely different signal than what you are intending to measure. So as an engineer, you have to know what is my sampling rate. For us, most of the signals that we deal with, there is not much of abrupt change. So moderate sampling rate will be sufficient. Now, we did the sampling. Now, my signal was like this. Now it becomes like this, samples, only samples. Now, these samples, this, for example, could be, this could be like 1.23 volt. This sample, 1.78 volt. Computer cannot read these things, cannot read these numbers. There is another thing that you have to do in the conversion process. Okay, to understand this, let's define 2 important terms. What is a bit? A bit is the smallest number in the digital system or the digital signals, and you have binary digits. You have either 0 or you have 1. Okay, so a bit is the signal element, which is the 0 or the 1. This is a bit, and this is another bit. Okay, so here we have two bits. Now, what is a byte? A byte is the combination of a bits. Now, this here will start to come to the resolution in your card. Okay, now this is, for example, an 8-bit. Okay, a byte composed of 8 bits. Okay, so I can have 0000 0, 0, 0, 0, 0, 0. Okay, or I can have 0, 0, 0, 0, 0, 0, 0, 1. 0, 0, 0, 0, 0, 0, 1, 0, and so on and so forth. How many combinations I can have of this until I reach to the last one, which is 1, 1, 1, 1, 1, 1, 1, 1. It is how many bits? You have 8. So it's 2 to the 8. So you will have 256 different combinations. Okay, that is your resolution. So your signal cannot be continuous, cannot take any value. It has to take the values between these, from starting from to the end, these 256 different levels. Only. You have only 256 levels. Your signal can be one of those 256. It cannot be in between. Okay, so this is what I said, resolution. How is good your card, how many bits it has, so that what is your resolution level? What is the minimum signal you can measure, as we will explain more. So what is resolution and what is the range? As I said, a range of the signal is what is the difference between the minimum, which is usually 0, to the maximum. So usually we have, for example, in your microcontroller, you have a 5-volt range. So your microcontroller, if you go for the analog input, it can only accept 5 volt. So your full scale range is 5 volt. 5 volt. That is the maximum. Now, your resolution is this full range divided by 2 to the power of the number of bits, which is how many possibilities you can have. And we will have here 2 simple examples to give you this more insight about this. So let's assume that we have only 1 bit. Okay, so you will have, so your n is equal to 1, so 2 to the 1 is equal to 2. So you have only 2 possibilities, either 0 or 1. That's it. Your card can give you either 0 or it can give you 1. This is the only numbers it can give. Now imagine that my analog signal is from 0 to 1 volt. You are measuring. Okay. Now I cannot see, for example, if my signal is 0.3 volt or 0.78 volt, how this can be transformed? It will be transformed to either 0 or 1. So if your signal is from 0 to 0.5 volt, it will give you 0. If it is from 0.5 to 1, it gives you 1. So you have only these 2 possibilities. And you can see the resolution is extremely bad, because anything below 0.5 volt will be 0. You will just see 0. Only if it exceeds 0.5, you will see only 1. So a signal of 0.6, a signal of 0.9 will be the same, will be only 1. Which is, of course, this doesn't exist, but this is just to start with. Now let's improve this. Let's go to a better resolution. Let's go for a 3-bit. Okay. Now a 3-bit, let's do the same thing. I want to measure from 0 to 1 volt. So my range is from 0 to 1 volt. That is my range. This is what I want to measure. Now I want to see what is the steps. What is my resolution here? Again, it is 1 volt. This is back to the previous formula, this formula, the full range divided by 2 to the power of n, number of bits. So 1 divided by 2 to the power of 3, which is 0.125 volt. Now I have a better resolution. Meaning, now from 0 to 0.125, I will have 0, 0, 0. So we now have 3 bits. Okay. Now, from 0.125 to 0.25, I will have 0, 0, 1. 0.25 to 0.375, 0, 1, 0. Now here, all of this range, 0.125, 0.25, 0.37 will give me only 0. But now I'm getting something different. So now I'm improving. I'm getting a better resolution. And so on and so forth, because we have here 8 different possibilities. So now you can see that the more number of bits I have, much better accuracy I can get. Now, none of the existing cards use 1 bit or 3 bit. That is very, very old, but this is just for the sake of the demonstration. So let's understand this as well. So this is my signal. My signal goes from 0 to 1 volt. From 0 to 1 volt. Okay. Now, ideally, I want to go through conversion from the analog to the digital using this curve, this line, the blue line. Okay. So for any number, I want to have a value. That is not possible. With this 3-bit, you have only 0, 0, 0, 0, 0, 1 until 1, 1, 1. So you have only 8 different levels. So if your signal, this is the same thing I mentioned in the previous slide, but you look to it in a different way. So from 0 to 1/8 of the signal, or 0.125 volt, you will get always 0, 0, 0, 0, regardless. If you go from 0.125 to 0.25, then you get 0, 0, 1, and so on and so forth. Okay, so now if you have better resolution, so you will have your car something like this. Now you have a better resolution. If you have more bits, so you will have something like this, which is much better than the one that you have. Please have all your questions. I will answer all of them at the end of the lecture. I will just go through all of them and I will answer them, because some of the questions you might hear them as we move on. Okay, so this is the 2-bit. 2-bit means 2 to the power 2, 1 over that. So this is 1 over 4.25. So this is your resolution. This is 1 over 2 to 3, or 1 over 8, which is 0.125 resolution. So if this is my analog signal, for 2-bit, this is what you will get. You have only 4 levels: 0, 0.5, 0.25, 0.5, 0.751. That's it. Okay, so you'll have these levels only. Now, 3-bit, you have 8 levels now. So you have much better than this, but none of them is good, of course. Now, the more bits, the more resolution you will have, the better your signal. Now, remember, this is not the sampling. The sampling has its own problem, aliasing, less sampling. Now, imagine if you sample the signal very well, still now converting this sample to digital, this is where the resolution comes. How many bits your card is using. Now, for your card, this card, it uses 10 bits. When you read, it uses 10, so it's 2 to the power of 10, which is 1024. So you have 1024 different levels. Okay, so I mean 1 over this. So this will give you the what is the small step you can go. And let's have some practical example. So if you have 8 bits, you have 2 to the 8, or 256 different values. 12 bits, now this is more of practical number of bits, 12 and 16. So you will have 4096 values, and this is 65,000. Now, most of the cards now, the recent ones are 16 bits. But for your card here, it's just only 10 bits because you don't need more than that. So let's see the implication of this. Imagine I have 8-bit resolution. So I have the first card, and my scale is 10 volt. Okay, so my resolution is 10, the full scale, divided by 2 to the power of 8, which is 10 over 256, and this is 39 millivolt. What does this mean? What does this 39 millivolt means? This is the minimum voltage you can measure. Less than that, it gives you 0. Okay, so if you measure 39 millivolt, this will give you 0, 0, 0, 0, 0, 0, 0, 1. Okay, so this is because it's an 8-bit. So you have here 4 and 4-bit. Anything less than 39 millivolt will give you 0, 0, 0, 0, 0, 0, 0, 0. So this is the minimum resolution you will have. Now, if I improve that to 12-bit, for example, 12-bit, again, 10 volt divided by the 4096, you get 2.44 millivolt. Now, the resolution is much better. 2.44 millivolt. That is the minimum voltage I can measure. Now, which one I have to use? It depends on my application. Assume I'm measuring something that the voltage is not that small. The voltage is, I'm measuring 3 or 4 volt. That is the range of voltages I'm measuring. Then that resolution will be much sufficient. But if I'm measuring 20 millivolt, my range is 20 millivolt only, then that's a bad, because always I will get 0. So it depends on my range. I can decide how many bits. But as I said, now recent cars 12 and 16 are very, very common. Now, digital input and outputs, as I said, now whatever I mentioned so far was for the analog inputs when I acquire the signal. And for us, as people using the cards for mainly for measurement, that is the most important application, that to acquire the signal. Now, why I need to send a signal? Sometimes, for example, I can give you a practical example. You are an engineer, environmental engineer, and you are measuring the moisture of the soil. So you have a moisture sensor. Now, this moisture sensor continuously will measure the soil moisture and give you the values. Now, you want to automate the process of irrigation. Now, once it reaches certain level of dryness, you want to turn on a pump. But you don't want to do it yourself. You want the controller to do that, the microcontroller to do that. So how it does that? It will send an output, a digital output, to turn on the pump, to make it working on, and continuously measure the moisture. When the moisture reaches certain level, then you send another output, digital output, to turn it off. And this is for the automation process. Now, we will, in this course, we will not concentrate on the activation, meaning that turning on and off devices that much, but we will more interested in acquiring the signal. Now, there will be a software, of course. Now you are acquiring the signal, you need to deal with the software. And there are tons of softwares can be used. MATLAB, for example, can be used. Unfortunately, MATLAB cannot be used with this microcontroller. We have to use the C++. Okay, and now this looks scary to some of you. Okay, we don't like programming, we don't like coding. You don't need to learn anything about coding because the codes will be provided to you. It is very simple, it's very easy to understand. You will do minimum things. So our objective here is not to challenge you in the coding, but in the application itself. So that should not be any of your concern. Shouldn't be concerned at all about that. Okay, so I will pause here a little bit. And let's see here if you have any questions. Let me go to the chat. Sure, I can go to chat from here. Let me stop sharing. And let me go to the chat if you have any questions. Because now, after that, we have a different topic. Can negative numbers be representative in binary? Yeah, yes, of course. They can be represented in binary. And the negative will be defined in a certain way. But we will not go that direction. But yes, of course, positive and negative number. So the plus and the negative sign, it will be assigned in a certain way to the computer. So more bits means the transfer function is closer to the ideal. Exactly. The more bits, you will have it more. We call it staircase, this one. So the better, the more, the better. Okay, excellent. So let me go back here. Sharing. Okay. So now let's move to the last part of today's lecture, which is measurement error. Now, if you noticed when I did the small clips about measuring the voltage, measuring the current, measuring the resistance, I will never ever get exact numbers. There will be always an error. Sometimes the error is big, sometimes the error is small. It depends. It depends on different factors. So if we want to represent that, how we can represent this. So if this is what you are measuring, this is what is the true value. Okay, so this is the true value, but this is what you are measuring. Now we don't know the true value. I'm measuring a voltage or a current in a circuit. I don't know what is it. Okay, so I'm measuring something. So there is a range, we call it uncertainty. Let's say I am measuring 10 volt. Okay, but this volt has certain uncertainty. It could be plus minus 0.1 volt, meaning that I am measuring 10 volt, but the voltage could be 10.1 to 9.9. It could be anywhere here. So it's very important to understand your uncertainty in the measurement. And I think in the lab, you will cover that in more of details, the uncertainty levels. Okay. Now, this depends on many factors. In your equipment, in your environment, there are many factors that will decide how uncertain is your measurement. But you have to understand that. Don't expect to get exactly the same number that in your measurement. I'm getting 10.56 volt. Oh, I'm getting 10.2 or 10.3 or 10.4 volt. Why? Because there is an error in the measurement. Now, the error, there are two main sources of error. And that's what will be ending my lecture today. There's one thing called systematic error. An error always exists. Okay? And sometimes we call it offset, sometimes we call it bias, because it offset the results. If my result is here, it's always there, always there. Okay? Now, why is that? There could be different reasons. One of the reasons could be from natural sources. For example, I am measuring the resistance, but the resistance value that is claimed by the manufacturer, let's say 100 ohm, okay, this is claimed at certain temperature, let's say at 25 degrees centigrade. Now, if you go and do the measurement under 50 degrees centigrade, you will not get 100, you will get a different value. Why? Because the temperature can impact your value. Now, someone may be laughing who says, are you kidding me? What is 50 degrees centigrade? I lived for a while in Dubai, and that was very normal temperature. Okay, even if you go like here, minus 25, like today, minus 25, the same thing. The value will not be 100. It will be a different value. So the environment, so you need to do this correction. You have to understand, okay, my measurement in this harsh conditions will impact my measurement. So if I don't pay attention, there will be always an offset, always an increase in my measurement. And this is a source of error that if I don't understand this, it will be always there and I can fix it. Sometimes improper calibration. We said that your sensor need to be calibrated because you need to convert what you measure into the actual measurement. You are measuring force, temperature, there is a calibration. Now, if the calibration was done in a wrong way, or sometimes the sensor age with time. So when you buy your sensor, it comes with, and I will come to this in the future. This is, for example, for the temperature sensor. These are some curves coming from the manufacturer to convert the resistance you are measuring into temperature. Now, this is coming from the manufacturer when the sensor was new. Now, as the sensor aged with time, this may not apply anymore. So there might be some aging that will lead to some sort of an offset. Okay, now you need to figure this out, and you need to maybe to recalibrate your sensor. Finally, it could be an error because of habits. You are measuring using a thermocouple at temperature, and instead of having, let's say, a specific distance, let's say 0.2 centimeter, you are, by mistake, you are having much longer distance. Okay, let's say instead of 0.2 centimeter, it is 10 centimeters. So this distance will impact the measurement, and you will have a bias in your results. The other type of error is a random error, not consistent like the previous one, but it goes up and goes down in a random fashion. Why is that? For example, if you are using this micrometer, this is we do it to measure a thickness of, let's say, sheet of paper, sheet of steel, something like that. Now, so you put the object here between these two terminals here, and then you press on it and take the measurement from here. Now, if you press too tight or too loose, sometimes tight, sometimes loose, then you will get different measurement. This is a random, especially if you are not an experienced person doing this measurement. Or you are measuring a voltage, instead of you having your probe at the exact same location, you are using different locations. So every time you are getting a different measurement. So this is a random error. Now, these errors will lead to three different important concepts. The first one is precision. High precision means that the random error is very, very small. But this doesn't mean that your measurement is correct. You could have a bias in the measurement, but there is no random error. Okay, so this is high precision, means your result is repeatable. Every time you do the measurement, you get almost the same measurement. Then you will have the bias. Small bias is something good, that there is the bias or the offset error or the systematic error is very, very, very small. What you want to have high precision, low bias, so that you will have accuracy, high accuracy. That's what you are looking for. So if you put, this is the last slide. If this is the bias, this is small bias, and this is large bias. We want to have small bias. Precision, this is low precision, and this is high precision. That's what we want. We want this, and we want this. Okay? Now, if we have low precision, large bias, and if I'm supposed to measure this, you see the results are scattered, random, and far away. So you have a high bias, and the results are not repeatable. They are far away. So you have a random error and you have a bias error. Both are there. But if you increase the precision, okay, but still you have high bias, then your results will be repeatable. They are close to each other, but far from the results. This is why I said high precision doesn't mean you have an accurate result. Okay, it means you don't have much of the random error, but you could have the systematic error. Now, if you go to the other hand, if your precision is low, but there is no bias or small bias, so you will have random error, but there is no, this random error is around the output because the bias is small, but still the results are random. This is what you want to achieve, the accurate results, where you will have small bias and high precision. So you do the measurement, it is okay, 10.2, 10.19, 10.18, 10.21, very close to each other. There is a little of randomness because you cannot have exactly the same thing, but it is very precise, and the error is, or the systematic error is very, very small. Okay, so that's what I want to say today. We'll stop the video.